One of the things we saw in Unit 3 was an energy profile, like you can see here on the screen. And an energy profile, again, is just a way of showing the energy of the reactants. It shows how much energy it takes. Remember, this right here is the activation energy. This from here to here is how much energy it takes to break those bonds. And then from the top all the way down, this is how much energy is released when the new bonds are formed. And overall, the energy change is from here to here. So in this case, this is another example of an exothermic reaction where the amount of energy released is greater than the activation energy, or the amount of energy it takes to break those bonds. Okay, and with elementary steps in a chemical reaction, you can also have an energy diagram. Okay, and this one, for example, is just showing one step in an energy diagram, but in an energy diagram with multiple steps, you can actually have multiple curves, which we'll see here in just a minute. Now, when an elementary step occurs, it can be one of three different what are called molecularities. Okay, it can be what's called a unimolecular reaction. In a unimolecular reaction, a single species, and you can't have more than one of that single species, that one single species will basically, it has to really decompose or rearrange itself. Okay, and when that happens, you can see here in the examples, you've got 1O3 breaking apart into O2 and O. You've got C4H8 breaking into two C2O4s. Notice that in each unimolecular reaction, there's only one reactant, and there's only one of that reactant. Notice down here in bimolecular, see how there's just one reactant, NO, but there's two of them? That's bimolecular. So when it's unimolecular, and again, we're talking about elementary steps here, so that when it's unimolecular, there's one reactant, and again, that reactant either has to decompose or rearrange itself, like you see here. Here you see it rearranging itself. That has to be a first order reaction, because we know we can use the stoichiometry of the balanced equation to determine the rate law. And so when there's only one reactant and there's only one of that reactant in that elementary step, it must be a first order reaction. Okay, in a bimolecular reaction, there are two species, two things that react. And they can be the same thing, like here, two NOs, or they can be two separate things, like an NO and an O3. Okay? And when they collide and they form the reactants, and again, we're assuming they're oriented the right way, that they're colliding, and that they have enough energy to overcome the activation energy barrier, those must be second order reactions. Because again, when in an elementary step, you use the stoichiometry, there's one NO and one O3, so those are both first order. So overall, that is a second order reaction. Or in this case, you've got two NOs, and obviously that's a second order reaction because there's two NOs. And then the third and really final and really very, very uncommon, we'll talk about that in just a second, are what are called termolecular reactions. And that is where three different molecules, in this case two NOs and an O2, would all have to collide with each other at the exact same time and with the exact right orientation, and all of them having enough energy to overcome the activation energy barrier. The more molecules that are involved, the less likely it is to happen. And even a trimolecular or termolecular is very, very uncommon because, again, remember, they have to collide, they have to overcome the activation energy barrier, and they have to be oriented the right way. And if one of those things are off on any of those three molecules, it won't happen. Okay, but if it did, you would have two and then one. That would be a third order reaction overall. So what I was just talking about is what we talk about here. The fewer the moleculars involved in the elementary reaction, the more likely it is that one of those collisions will be the correct orientation, meaning that it has enough energy to overcome the activation energy barrier, and the chances of correctly oriented collisions will go down as you add more and more molecules to that. Okay, again, those trimolecular ones are relatively rare, since for a trimolecular, they have to be, again, colliding at the same time with the correct orientation and with enough energy to overcome the activation energy barrier. Again, the likelihood of all three of them being exactly where they need to be, colliding at the exact same time, all with enough energy, is, again, usually not very high. Now, like we talked about earlier, when you have multiple steps in a reaction mechanism, you can have a curve that shows different each step. So here would be step number 1, here would be step number 2. So notice that step number 2 just basically takes over where step number 1 ends. So you've got this, again, activation energy to get to that transition state, that where the bonds are broken but the new ones haven't formed yet. And then you release that energy when the new bonds are formed. And then again, now you're into step 2. Now you got to break some more bonds. And then you got to form some more. You got to release some more energy when those new bonds are formed. And overall, the overall energy change for the reaction would be from here all the way down to there. Okay, and in this case, yes, both steps are exothermic reactions, but certainly they don't have to be. Okay, you absolutely could have one that's exothermic, one that's endothermic. Just the way that these are drawn, you can see clearly that both of them are exothermic processes. Okay, let's look at some examples here then. For a reaction between X and Y in the equation below, data has been collected in the table. Is it likely that the reaction takes place in one elementary step? If it did, how many molecules would have to hit each other at the exact same time, oriented the right way, all with enough energy to overcome the activation energy barrier? 5. Okay, so there's unimolecular, bimolecular, trimolecular. So then there'd be like whatever 4 would be, and then whatever 5 would be. Is it likely that all 5 of those hit each other at the exact right same time, forming Y2X3? Absolutely not. Okay, so I would say no, and you would say because 5 molecules, they'd have to be oriented correctly. They'd have to hit at the same time and all have enough energy to overcome the activation energy barrier. I'm kind of summarizing here. Okay, the likelihood it basically is not likely. Okay, for all of that to happen. Okay, and then B says, a student looks at the balanced equation above and deduces that the overall order of the reaction is 5th order. Explain the error the student made in determining the overall order of the reaction. Okay, because you can't use the stoichiometry of the overall balanced equation to determine the order of the reaction. Okay, you have no data that tells you what the order of X is and what the order of Y is. Remember, only if it's an elementary step. And remember, guys, at any point when I'm explaining an answer, and like on part A, when I don't write all of that out, I'm just trying to save time, I would strongly recommend that you stop and pause the video and then you write out your answer. So on B, I would say something like, explain the error. I would say this: you cannot determine the order of a reaction based on the overall balanced equation. And if you wanted to add a little more, you could say you can only do that with an elementary step. And so you can't do it with an overall equation. There's no data to support that X is 3rd order and Y is 2nd order. Okay, part C says, all right, we'll give you some data. Using the data table above, determine the actual order of each reactant to justify your answer. So notice again, we've got our balanced equation up here. We really don't even care about it. Now that we have the data, now we can go, okay, well, in trials 1 and 2, and again, I'm kind of summarizing here just to not waste your time while you watch me write everything down. So I would say something very similar to this. In trials 1 and 2, the concentration of X doubles, the concentration of Y stays the same. The rate goes up by a factor of 4. Therefore, X is absolutely 2nd order. And again, if that's all you write, you are absolutely not going to get credit. Okay, you write what I just said. Start on this side and basically just make your way this way. Okay, and then for Y, I'm going to say in trials 1 and 3, X stays the same. The concentration of Y decreases by half, and the rate does not change. Therefore, Y is 0 order. Remember that if the concentration changes and the rate doesn't change, it's because it's 0 order. And again, why is that? Because probably in one of those steps of the reaction mechanism, which we don't see and we don't care, but y is in one of those steps, but it's probably in one of the fast steps, not the slow step. Okay, and again, we don't have to explain that, but that is probably why y is zero order. Okay, and so the rate law for the reaction is going to be rate equals K times the concentration of X squared. Again, leave y out altogether because it's zero order. Determine the overall order of the reaction. Of course, it is second order because of that right there. And then it asks us to find the rate constant. It's been a little bit since we've done this, but now we have the rate law, so we're trying to find K. So we're going to choose any of those three trials. I'll just choose trial number 1, and we'll say that the rate is 1.00 molar per minute is going to equal K times the, and again, usually I use regular parentheses when I put numbers in. So it's 0.00500 molar, and that is squared. Okay, and so now to find our answer here, we're going to take 1.00 and divide by 0.005 squared, which is a very, very large number. K is going to equal, and again, it looks like everything has 3 significant figures, so I'm going to use 3 significant figures. 4.00 times 10 to the 4th. Now, in terms of units, we're going to have minutes on the bottom because you always have time on the bottom. So definitely minutes to the -1. This molarity is going to cancel with 1. Remember, this is molarity squared. Don't mess that up. So that molarity is going to cancel with one of those molarities, so you are left with 1 molarity. So it's molarity to the -1, minutes to the -1. Okay, example 2. Write the overall reaction. So here I'm kind of looking, I'm trying to find catalysts and intermediates, things I can cancel out. Looks like I made 2 CLs. Okay. And then I used a CL here and I used a CL here. Does that count? Absolutely yes. Even though they're in different steps. Cancel, cancel. Okay. Let's see. And that looks like we make a CCl3 here and then we use it again. So CL is an intermediate in both cases. And I think that's it. So our overall equation would be Cl2 plus CHCl3 making HCl plus CCl4. And it looks like, yeah, basically we've traded, one of these chlorines and hydrogens have traded places. And yes, it is balanced, so it's good. Okay, catalysts, there are none. Intermediates, so the intermediates would be Cl and CCl3. What is the molecularity of each of the elementary steps? So step 1 has 1 Cl2, so that's unimolecular. Step 2 has 2 different reactants, and there's 1 of each of them, so that's bimolecular. And then 3, also same thing, bimolecular. Okay, which step is the rate determining step? Basically, that means which one is the slow step. That is step number 2. How do I know it? Because it says it. And then E is the tricky part. E is the, now you got to write the rate law. Okay, so let's kind of go through this. This is good practice here. The rate is going to equal K times the concentration of CHCl3, which is good. That is in the overall equation. And Cl, right? But Cl is an intermediate, and it comes back up here. Okay, so what do we have to do? We have to go back to the previous step, and we're going to set each side equal to each other. So that means using this top equation up here, we're going to say the concentration of Cl2 is equal to the concentration of Cl squared. Okay, but notice in our equation here, we just have Cl. We don't have Cl squared. So when we replace Cl with something else, it has to be, this equation has to be set equal to just Cl, not Cl squared. So how do you get rid of a square? Of course, you take the square root of it. Okay, so yes, we have to take the square root of both sides, and what that's going to do is that's going to get rid of that squared there. And when you take something to the square root, that's the same thing as raising it to what power? of course, the 1/2 power. So Cl, the concentration of Cl, is equal to the concentration of Cl2 to the 1/2 power. So what does that mean? It means now I can replace it. Now, instead of this, I can replace it with whatever it's equal to, which is one of the very, very few times, probably literally the only time I've seen an order of only 1/2. Okay? So, and that is the correct answer. That is, the rate is equal to K times the concentration of CHCl3 times the concentration of Cl2 to the 1/2 power. Okay, and again, remember, all I'm doing, guys, is I'm following the rules that I've learned. Oh, wait, I've never seen something like that before. They try to mess you up on the AP test by giving you things you haven't seen before. And they make, wait, what? Okay, one more here. I think it's the last one. Yeah. So, last one. So, in example 3, we've got a hydrocarbon, blah, blah, blah. We've got a slow step. We've got a couple of fast steps. So, again, write the overall equation. This is kind of a mess. So, make sure when you cancel things, you cancel things that are exactly the same on both sides. So, again, if I were you, I would pause it at this point, and I would make sure that I make this, try this, do everything you can yourself, and then come back and then watch me do it. So it looks like in step 1, we make CH33AU, and then we use it again in step 2. So that cancels. PH3 gets made in step 1 and then used again in step 3. Let's see. CH3AU gets made in step 2 and then used again in step 3. And I think that's it. So our overall equation would be this CH33AUPH3 making C2H6 plus CH3AUPH3. Okay, and that is the overall balanced equation. And yes, that is correct. Identify the intermediates or catalysts. Again, no catalysts in this one, so the intermediates would be, of course, the CH3AU. And then the PH3 is also 1, and then just the CH3AU is also 1. So you've got 3 intermediates in that one. Which step is the rate determining step? Obviously, that's step number 2. Why? Because it's the slow step. It's the one that determines how fast the reaction goes. There's nothing else that you need to say other than that. Write the rate law for the reaction. Okay, here we go again. So our slow step is step number 2. So again, the rate law should be rate equals K times the concentration of CH33AU, close parentheses. But then right away you recognize, oh, wait, that's an intermediate. I can't have it in my rate law. So again, make this easy on yourself. Just right away set both sides equal to each other as if they were both rate laws. Okay, so that means that the reactant, CH33AUPH3, is going to equal the concentration of CH33AU times the concentration of PH3. And then again, we've got to get CH33AU by itself. So to get it by itself, what do we have to do with the PH3? We have to divide it. Okay? And so instead of CH33AU, we're going to have this divided by the concentration of PH3. So what do? I go back in and I basically start over. So it's going to be the concentration of CH33AUPH3 over the concentration of PH3. Again, trying to give you some crazy, weird possibilities that have been on AP tests, just so when you see something like this, you're not like, oh, I don't know what to do. Okay, that's what you have to do. You're just following what you've learned to do. And then part E says, what would be the effect on the reaction rate of adding pH3? Well, if I add pH3 is on the bottom of my fraction. If I add some more pH3, that makes the number get bigger. If the number gets bigger, what does that do to my rate? Of course, if the denominator in a fraction gets bigger, it makes your answer smaller. So what effect would it have? It would reduce or lower the rate. And again, you would want to explain because an increase in the concentration of pH3 makes the rate go down.